When a version of the Monty Hall problem gets published in one of our puzzle books, it always leads to some people writing in saying that the answer given at the back of the book is wrong, with various different levels of outrage. So we thought we'd do a video about the Monty Hall problem to explain what it is, why it leads to such bafflement for some solvers, and also as a point of reference that we can point people to in the future when a puzzle like this or based on this gets published in one of our books to explain exactly how it works. So what is the Monty Hall problem and why is it counterintuitive? Well, let's have a look. Okay, so there's various different setups and the exact details don't matter too much, but here's a common setup. So you imagine you're on a game show. You've got 3 doors that you can't see through. Behind one of the doors there's a prize that you really want. Typically it's a brand new car, but of course it could be anything. Behind the other 2 doors is something that you don't want. In this version of the puzzle, it's goats. Poor goats. So the setup is simple. There's 3 doors. You want to win the car, but you don't want to win the goats. So the first step is fairly straightforward. You have to choose one of the doors. If you get it right, then you win the prize. If you don't, then tough luck. So what's the probability that you choose correctly? Assuming everything is completely random, you can't see through the doors, you've not been given any hints, then so far so straightforward. Everyone agrees you've got a 1 in 3 chance, that's 33% roughly, of getting it correct. But now comes the interesting twist and a follow-up question, which is where a lot of people find this quite counterintuitive and are convinced that the explanation is wrong. So let's have a look. So imagine that you open door 1. Or you choose door 1. You don't open it yet. The host, who knows what's behind each door, opens door 2 and shows that there's a goat there. The important thing is that the host knows where the goats are in advance and will always pick a door with a goat. So if you'd picked door 3, they could have picked door 2. If you picked door 2, they could have picked door 1, assuming that they know where the goat is. But they will never reveal the door that has the actual prize, the car behind it. So now here is the important question, the key question really, and this is what causes confusion. Do you want to stick with door 1 or switch to door 3? So we're currently in a situation, and again, there's nothing particularly special about the doors, but you happen to have picked door 1. You don't know if it's right or wrong, but you do now know new information. You now know that door 2 does not contain the car. It contains a goat. And so the question is very simple. If the host offers you the choice of switching your choice from door 1 to door 3, what do you do? Do you stick with door 1 or do you switch to door 3? If you've not come across the Monty Hall problem before, or you want some time to think, then pause the video here before we move on to the next slide. Okay, so a common intuition is that there's only two doors left, so it must be 50-50. Therefore, it makes no difference at all whether I stick or if I switch. It's like flipping a fair coin, heads or tails, makes no difference. This intuition is wrong, and this can be very confusing, particularly if you've not had time to see this puzzle before and to think about it. So on the next few slides, we're going to try and explain clearly why this is wrong and why you should actually always switch if you want to win the car. And this is why. If you look at the actual chances that are now shown on this slide, you can see that your original door has a 33% chance, a 1 in 3 chance, which you knew already. But that means since probabilities have to add up to 100%, and we know that door 2 is now 0%, then door 3 has 100 minus 33.33, which is 2/3 probability. So the key insight is this: the probability that's behind door 1 doesn't change. It stays at 33%. And all the probability from the other 2 doors is now behind door 3. This means that switching actually doubles your chances of winning. So if you want the car, you should always switch in this scenario. Let's have a look in a bit more detail. So probably the most important thing to note is that the information that you get about the setup increases. Remember at the start, we just had 3 doors. We didn't know anything at all. Now we have new information. We know that door 2 doesn't have a goat behind it. So initially we know your door has a 1 in 3 chance of being correct, door 1. That means that in that setup, the other 2 doors had a 2/3 chance which is just 1 minus a third, because again, the probabilities have to add up to 1. So when the host eliminates one of those doors, in this case, he's taken door 2 out by showing there's a goat behind it, all of that 2/3 probability transfers to the remaining door. So another way of thinking about it is this. The host is essentially asking you, do you want to stick with your original choice or take both of the other doors? Now, if you were offered that up front, you can have 2 doors or 1 door. Obviously, you take both because it doubles your chances of winning. And so when the host removes the goat from the other doors group, which here is just door 2, you effectively get both doors when you switch. So hopefully that makes more sense. Hopefully you can find that intuitive, that if you have effectively now, do you choose just door 1 or do you choose doors 2 and 3? Then I think if it's explained like that, most people would obviously pick the option where they get to open 2 doors for the price of 1, literally. And just to really hammer it home, I'd say there's nothing particularly special about the setup with 3 doors. You could imagine there's 100 doors. And perhaps this intuition can help some people understand it as well. So let's say you pick 1 door. You pick door 1 to make things simple. Everybody agrees that if there's 100 doors, you have a 1% chance of being right. And I think everybody also agrees that the other 99 doors have a 99% chance combined, because 1 minus 0.01 is 0.99 or 99% chance. So if the host now opens 98 doors, all of them with goats behind it, then there's 1 door remaining from the other 99. Would you switch in that circumstance? I think here most people would say yes, and therefore if you follow the logic through, you realise that remaining door has 99% probability, so you definitely should switch. And so to sum up, if you kept with your original decision, if you stayed with door 1 in this scenario, then you'd only win 1/3 of the time, whereas if you chose to switch, then you'd win 2/3 of the time. Therefore, switching gives you twice the chance of winning. And if you still don't believe that, then rest assured that computer simulations are very easy to run of this, and they show that if it's run enough times, then the probabilities do indeed tend towards a 1 in 3 chance if you stuck with your original decision, and a 2 in 3 chance if you switch. So it's definitely true that you should always switch in this scenario, which we've labelled here the surprising truth. Hope you found this video useful. If there's any other puzzles or paradoxes that you'd like us to talk about on this channel or try and explain, then please do let us know. We'd love to hear from you in the comments, and please do like and subscribe to our channel. Thanks for watching. See you next time. Bye.